much.
Sure thing. Hello, everyone. So, we're starting here. This is going to be a little higher level talk than what you've heard. We're not doing satellite signals. We're not doing, we're not hacking hardware directly in this conversation, but we're going to talk about the operations layer, right? How do we get code deployed, and what do these clusters look like? So this is kind of a brief history of who I am. I've spent about 30 years being a technologist within Hollywood. So we have Hollywood A-level content, potentially billion-dollar assets that we're trying to protect. In the old days, we typically relied on air gaps and shipping hard drives around. While that is relatively effective, it is not very efficient. And the funny thing about Hollywood movies is that every movie is basically a new company that starts from the ground up, assembles a team of people, the editors, the visual effects artists, the shooting, the entire production crew, the production company that's operating it, right? Everybody's all separate. They're all separate individuals, separate companies, all trying to work together to produce a movie. And therefore, we need to communicate, right? That's just fundamental to what we're doing. But they had such restrictions in place, it really made it difficult, and it was absurd, some of the stuff that we had to worry about. But that's changed. We understand that we have to be in a connected world. We have to deal with larger clusters. So all of my background is high performance computing. How do we do this in a secure manner? We had about 10 petabytes of content at Technicolor, running 75 feature films and broadcast series simultaneously, with data centers in London and Hollywood all being run by my team in LA, right? That's the kind of stuff that we're building, just to kind of give you an idea of the scope and the amount of data that's moving around. And as an example of a workflow, one of the things that happen is your editor has your movie all set up, and now you just say, this shot has visual effects on it. So the editor needs to mark that shot and say, now send this to that visual effects company that's the separate company that we talked about that's going to be doing that work. How do we send that material? Well, they make an edit list, and they send it to the post-production company that is holding all the assets, and that gets processed through some processing systems, and then it gets transferred securely over to the visual effects company. That process would take a week before we deployed our system, right, with all the people that had to write work orders and send them between departments. Now it's a 3-hour process, and it's all self-serve, right? I mean, that's the advantages that we get out of having cloud computing behind the scenes. So I've been involved in a lot of that stuff. And these days, I'm doing a lot of work with zero trust architectures, trying to figure out how we can make this stuff more integrated and allow teams to communicate and work together. One of the tools that I've been using for about 5-ish years, I would guess, is Kubernetes behind the scenes. And for those of you who aren't necessarily familiar, Kubernetes is a container orchestration system. What does that mean? Well, run a container. But there's more than that, right? How do we do scaling? How do we do deployments without having downtime? All those are aspects that Kubernetes tries to take advantage of, which is great. I mean, that gives you a ton of capabilities and features, but also adds a significant amount of complexity, right? So these are the benefits, right? Kubernetes gives us a consistent view of what the hardware looks like, right? We basically get to say, deploy a container, don't worry about what the system looks like, right? It will do the right thing, it'll find the disks, it will, it'll create networking interfaces, it'll do all that stuff. As I said, it automates many of the hard parts of your DevOps problems, right? The corner cases, right? When you want to upgrade the system, how are you going to do that? How do you migrate the jobs to a different machine? How do you update the code base without having downtime between them? How do you manage storage? How do you do scaling when you all of a sudden have a load that you didn't expect, right? So Kubernetes is trying to solve all those problems for you, right? Which is great. They're really useful things. And then as a personal thing, I think a big benefit is this configuration as code, right? Because the more consistency we have, the less likelihood that there are errors where a system admin forgot to set something up on a system, so it either doesn't work or has a security issue, right? We can check in the code, we can track all the changes to it. That allows us to do audits, that allows us to automate this entire process. So configuration of code and automated GitOps kinds of features are really great for what Kubernetes brings to the table. But that asterisk at the bottom is really important, because I'm going to say this. Kubernetes is the hot new thing. I guess it's been around for a while, but you may not need it, right? I mean, just for people who haven't looked at this, you may not need Kubernetes, right? You can do a heck of a lot with one box that runs in the cloud and provides a bunch of systems, and you can scale that box up to lots of CPUs and lots of disks. So maybe you can just run on one box and do that. So always think about whether the complexity of Kubernetes is worth the hassle and risk of the rest of the process. Okay, so we're going to start with, you need a Kubernetes cluster. Any of your cloud providers can provide this. They all do it as a service, right? Elastic Kubernetes service is the Amazon one, but every single cloud vendor has one. You basically say, here's the nodes I want, the configuration I want, bring it all up. And what they will hand you at the end of that is basically an admin token that you can now use to talk to this cluster on the, directly once it's running. There are other ways to do this, right? If you have edge computing or you've got your own data center and you want to run this, there are easier solutions like K3S is a relatively small one. You can run on a small bit of hardware. I have a K3S lab in my house. Micro K8S is another architecture for doing this stuff. Also with Kubernetes, you're going to find that there are multiple choices for virtually every way you're going to configure any piece of the system. So I'm not going to try to list all of them everywhere, but give you prototypical examples that you can look at and think about. If you want to get all the way down to your laptop just to play around and do development aspect stuff, Kind is Kubernetes and Docker, and Minikube are both tools that you can basically run on your laptop. It'll set up an entire cluster on your laptop for you to work with and play with and learn from. So really useful tools for doing this. So what makes up a cluster, right? We have worker nodes and we have control nodes. The control nodes are the pieces that you're going to talk to when you use the Kubernetes API or when you use the kubelet application on your machine. That's how you talk to your cluster and configure it and do all those sorts of things. And the worker nodes are where your containers are going to run. And worker nodes can be separated into multiple different. You can have multiple different kinds of them in different sizes and types, and you can label them so you pick the right ones for your setup. Beyond that, you also tend to need a bunch of other services, right? So I probably want to have an object store. Well, that's going to be another thing. It might be running in my cluster, or it might be running outside of my cluster. I might need to have some other hard disk storage. I might need to have some ephemeral disk that shows up in my workstations. I might need to have some tunnels and other networking things. So there tends to be a bunch of other pieces that are sort of outside of the strict definition of what is Kubernetes, but are needed to make a cluster actually be useful. So I'm going to roll those into the picture here. The node itself looks something like this, right? You've got a machine that's got some CPU and some storage, right? Has some networking capability, and it runs this thing called the kubelet, right? That's the main Kubernetes control process that's on the box, right? You should pretty much never see these things. That's in there, this is in there and running, but you don't typically interoperate with it directly. You will need to configure it to do all the things that we're going to do in this process eventually. And then what kubelet's going to do is it's going to launch processes in a Linux namespace, right? So that we can isolate those processes and separate them from the rest of the system. Beyond that, what Kubernetes calls a pod is basically a collection of containers that are running, right? And interoperating together. And that vertical line that I drew is a namespace in Kubernetes. We'll talk about that in a second. But that allows you to do some separation, sort of a label on the assets that are running inside of your Kubernetes cluster. So, and then like I said, the kubelet is going to use whatever the fundamental hypervisor on your system is using in order to launch those containers. That could be the open container system, or that can be Docker, whatever your mechanism is that's in your OS. So my systems are Linux-based systems underneath, and I'm running K3S on top of them, and I'll show you in one of these pictures coming up, I'll show you what that looks like. No, actually, I'll show you on this was the previous one I showed you. So that's my little home cluster, right? So the one on my left is not actually part of the cluster itself. It's the file server that they're all going to use for shared storage across my nodes, right? For anything that I want to be persistent, right? Needs to live on that. I've got two little mini PCs in the middle there. Those are little AMD boxes with 6 cores and 12 threads, and they have a little ephemeris NVMe disk that I use for ephemeris storage. There's an ancient networking switch under there. And then there's one bigger node that I've labeled, and that has a GPU in it, and it's got more storage and some other things. So if I have any big jobs, I will force them to run on the big node, and then I've got the 2 small nodes that are basically for anything else, right? You give or take a couple gigabytes per CPU, and you can kind of divide that up. So the first part of this, we got to worry about container security. Now this is the higher level stuff. I'm not going to spend a lot of time on this, but anytime you run a container, we care about all these pieces, right? So make sure you're using trusted images in the containers you're going to run, right? set a user inside of your container, right? It's really not good to have them running as root. Little 2 lines of Docker script that you would use to build those containers to create a user, to add a user to your environment and switch to it after you've installed all the system, all the applications you want to install on it. Reduce your DAC surface in whatever application you're going to run, always a good thing to do. Keep your containers up to date, right? If there are security patches, you want to get them in there. Utilize the scanning tools that are available to you. There are static and container. There are code analysis tools and there are container analysis tools that will check those containers for you. And again, verify the supply chain as best you can. We're all building on top of lots of layers of applications, so you want to make sure you have those checked the best you can. All right, so there's a container out there in the world, and you've got a cluster, you've created it in the cloud, you created it on your own workstations, we're ready to go, right? So here's the basic script, right? What are you going to do here? The first thing you're going to do is we're going to run this image called Nginx, right? So I can go to Docker Hub and I can look it up, and Nginx makes that container and will always be up to date, et cetera. So boom, pod Nginx has been created, right? The next line there says we're going to expose the Nginx port 80, right? So that just made the pod available, exposed that port on that pod within the cluster, right? That's what that piece did, right? And then the last bit there is I ran what's called an ingress, right? And that says I want to take the name k8s.local, right? And I want to drive it to my Nginx pod, my Nginx service 80, right? And now I've got a way to connect to my pod from the outside world, right? I can connect to it from my own machines, or I can, if this is on the public internet, that could be exposed and that would make it available, or you could put a load balancer in front of it, or you can tunnel it. I happen to use Cloudflare tunnels for my stuff in my home lab when I want to expose them. But, that's the basic, you read any Kubernetes, documentation, that's what they're going to tell you to do. That's those 3 steps, right? Here's a little bit of a problem, though. Oh, okay. Look, Ma, right? We have an exposed service, right? We're up and running. It's been running for 51 seconds, and there's my service that's been running for a little while, and there's my little web browser. I have connected to Nginx, right, inside my from outside my cluster, right? I just went to the k8s.local IP address that I have in my etc host file, right? And lo and behold, there's Nginx running. Okay. So there's some interesting stuff. So what did that actually do, right? Now this is one of my denser slides. I will talk through it a little bit here. But what you see here is the YAML definition of that pod. Okay, so these can be text files. When I told kubectl to just run this, what it did was make a default version of this YAML file for me, right? And this YAML file says that the service I'm running is Nginx, and it's using the Nginx container, and the image policy is always, so it's always going to fetch the new container from wherever my container storage is. It has some stuff about resources, and it mounts some volumes, right? And there's some security context stuff, and there's a default service account that happened. All those things got created for me by default. Much of that is not great, right? Much of those defaults are easy, but they are not really the best way to be running this thing. That resources was just set to empty curly braces, right? So we did nothing to tell Kubernetes what sort of resources this pod should use. So we have 2 aspects down there that we can add to the resources fields, right? The first thing is the requests, right? So that basically tells Kubernetes, hey, when you're scheduling this job on those 3 machines that are in my little home cluster, what do I need, right? Do I need the big box that has all the extra RAM and the GPU, or can I get away with the little box, right? And how many of these can I run on this box, right? If you run the box out of memory, right, it does not perform well, and all types of bad things happen, right? So this allows me to, the request level allows me to say, this is what you should be providing for my application. Now, that's not a hard limit, right? So I can go above that, right? It will just try to schedule things out based on what you gave it, but once it's running, it's not going to do anything to stop it. So that's what that second column is, limits, right? So the limits will actually restrict the amount of CPU cycles that I get and the amount of memory that I get, and will kill the process if I run over the memory limits, and will restrict the CPU cycles to that many CPU cycles, so my application will slow down In fact, it'll always slow down. It'll always be restricted to that level. But I can be guaranteed that I won't use the particular node that I'm running on. So that's pretty good. That helps, right? So our security context was also set to nothing, right? And that basically means I'm just going to trust whatever that container told me, right? So if that container is running as a root, then everything in that container is, if you didn't specify a user, everything in that container is going to run as root. So again, as the operations guy, I want to make sure that my developer didn't do something dumb or just restrict the access in general, right? So I can say, this is not going to be a privileged container. It has no additional capabilities on the box. I can say that it should never run as a root user. I can say you can never escalate from the default user to root, right? I can say that there are no other extra you shouldn't allow any extra capabilities. You can layer them. Privilege gives you everything, and then capabilities gives you individual capabilities in the Linux kernel that you can add on. So if your app needs to call ping, then you're going to need the network privileges to do that. You could add that one capability to the system and have the ability to call ping. There are a few other choices here on the right-hand side. You probably need those less, but you can force the container to run as a specific user, right? That can be useful. Often the configuration when the container was made kind of assumes what user it's using, so that can be problematic, but you can do it. If you have security enhanced Linux on your system, then you can pass all the context information to set up a security enhanced Linux context and make your pod run in that context. If you have seccomp profiles or Windows options, also give you some more of those authorization capabilities in the pod that you're running, right? So you can lock this thing down pretty darn far if you need to for this one pod. Right? So those are all the options for controlling a single pod. That's the YAML that we got by default for our ingress, right? So it's an ingress, it's called Nginx, and it's using the 3 nodes that are in my little cluster at home, and that's all it specified, right? There's a spec on the right-hand side that says my ingress class name is traffic, right? So that's one of the multiple choices you have for ingress on a Kubernetes cluster. Your ingress controller is the thing that is going to route that traffic from the outside world. It's going to look up the host name that it was assigned to when we pass the ingress in. Or, I mean, right now the ingress is to the outside of the box. The load balancer would deal with the name, but that's the host name that it's going to map, right? And it's going to map it to a specific path and a specific service, and that's how it's going to get to my Nginx controller, right? So, again, really useful. That's a good thing, right? But again, by default, the way I did that, that ingress is unencrypted, right? So we can pass a TLS parameter in when I create the ingress, right? So that's one option. You would have to already have made your certificate for your TLS in advance, added that as an object into your Kubernetes cluster, and then use that when you created the ingress to say, you pass an extra parameter called TLS that says, here's the ingress to go use, right? So that's great, that works pretty well, but we have a better answer, which is Cert Manager, right? So Cert Manager uses Let's Encrypt and just automatically creates them, and in fact automatically updates them when they need to rotate and all those other great things for you. It's a wonderful tool. A Helm chart will deploy that into your cluster, and then instead of passing in when I create the ingress, there's a couple annotations that you put at the top of the ingress that say, use Cert Manager and add your certificate to that machine. So far, pretty good. We're making progress here, right? We've at least locked some of this stuff down. The next problem you run into is secrets, right? Virtually every application you've got needs some sort of secrets, right? If nothing else, you're probably going to talk to a database somewhere back on the back end, and you want to store that stuff. So on the left-hand side, we have the text, the YAML definition of a secret, right? In this case, I'm telling it that my SQL alchemy, right, that I'm going to use for my database access is an SQLite database in the data app DB file on the system. And on the right-hand side, I've modified my pod definition now to say we're going to use the environment to pass in the SQL Alchemy URL, and we're going to pull the value to use in that from app secret SQL Alchemy URL, right, parameter. So that's how it's going to get in there. So it's going to be an environment variable, right, and then my code is going to go look for it as an environment variable. The other way you can do that is you can mount the secret as a file system, as a directory in your file system, and you can read the file that way. That's just another option for getting it. But you know what? When you look at the system, once it's in there, secrets really aren't really secret, right? I mean, if you can get to the API, right, of the Kubernetes system, you can basically just go ahead and output the YAML for the secret, and there it is, right? So anybody who's got access to the API can go get all the secrets, right? It's just base64 encoded. So no matter what you're doing, secret management is hard, right? It always is. Obviously, don't include secrets in your containers. We've already talked about containers, but don't do that, right? We can get them through environment variables or through mounting the file systems, right? There is an advantage to mounting them through file systems, which is that we can rotate them and change them. So as long as your app knows to recheck that every once in a while and see that the files have changed, the file system mounts can be dynamic, and the environment variable is just once when the pod starts up. So that could be a useful feature if you have that capability. There are some nice secret management services that you can run inside your cluster or elsewhere, right? HashiCorp Vault or the open source version, OpenBow, basically allows you to stick the secrets in the vault, and then it knows how to insert those into the pod for you as file system entries, et cetera. The other interesting bit about secret management is, like, now you've got these secrets, how do you make sure that your right people in your team can get them but the wrong people can't, right? You don't necessarily want to share your secrets with your entire development team. Your ops team might want it. I kind of like SOPs. Basically what that does is use a GPG key to encrypt the secret, and then you can check that into Git and share it among your team, and only the right people have the GPG key to decrypt it. And then when it gets added to the cluster, SOPs automatically does the right stuff to decrypt it and push it in. So that keeps it entirely in your DevOps teams. So secret management, always an issue, but we can deal with some of that. Everything we've done so far is in the default namespace. And the default namespace is default. But that gets crowded, and that doesn't let you separate anything. And as we get into some of the role-based access control, you really need to start using namespaces for stuff. So another thing we're going to do is add a namespace to that, to everything that we're adding to the cluster. Every time we put an item in, we're going to put a namespace on it. If you poke around, you're going to see other namespaces already exist in your cluster, right? So you'll see the kube system namespace, and there's probably a bunch of stuff in there that were things that were launched in your cluster by default. Whichever sets of batteries included were with your whichever distribution you're using for Kubernetes management. And like I said, we're going to use them for role-based stuff. So the next issue we're talking about, the next issue that we walk into here is, our developer is happy, but now he wants some more friends, right? He wants some more people to work on the system together, right? We really shouldn't just give him API access to the cluster, right? We really want to start separating this stuff, right? And controlling what access individuals have. And if you have that token, there's no differentiation of who that user is, right? It's just a token that's being used. It was handed to you when you created the cluster. Unfortunately, user management is outside of Kubernetes. Right, so it can be configured to access certain pieces of data for user management, how to interpret the token it's given, but it doesn't do the management of users itself in any way, shape, or form. You can do an X509 certificate, and it will use the common names, a CN parameter in the X509 certificate to identify who the user is, and then it will do the role based on that, right? But it's not managing the users. You can set up OAuth 2 and then tell the kubelet to use OAuth 2 to do it, and then you can use whatever provider you want to manage all that. You can run a user management system, so that could go to Google or Microsoft or your own systems within in-house that are doing OAuth, right, single sign-on solutions. You can run Keycloak, which is an open source OAuth 2 management system, right? Now that lets you manage users and separate them into realms and have multiple applications with different users. A lot of cool features in Keycloak for managing lots of users. Again, open source solution. Many of these can run in your cluster, and then your cluster can use them themselves. So now we can figure out the identity of the user. And we're going to do role-based access control, right? So the role-based access control is made up of two parts, a role, and there are a bunch of default roles that come with your cluster, and then a role binding that basically says, now that you've got this identity that we found earlier, looking at that common name or looking at what the identity parameter was inside of your OAuth certificate, or OAuth token, right? You can now map it to a role, right? So those are the two pieces you're going to look at, is the role and the role bindings, right? And those can be in a specific namespace for a role binding or over the entire cluster. So now we can start doing things that are useful. We started moving all this code so the user is not deploying everything into the default namespace. You've given the developer a single namespace, and now you can start creating roles that basically say, in this namespace, you can view all the stuff in this, but you can't modify it. Or you can limit access to, or you can give them some modification capabilities, but limit it to specific resources within Kubernetes, right? Don't let them see the secrets, but they can see anything else, maybe, right? Again, there's a combination of verbs of change, read, write, etc., create, and the resource in Kubernetes that they should be able to operate on. That's what goes into the role, right? And then the binding is what assigns that role to a user. So great, our little team is cranking along, and they still got a lot of access, but we've at least limited who can do what, right? And we've separated the teams a little bit, but now we're going to get a little more sophisticated. We're going to add some DevOps guys, right? So now we're going to really separate this functionality, right? The developer just writes the code, builds the container, he's done, right? The ops team, the DevOps team, is going to do the rest of the process here and manage the actual deployment of that container into the cluster. So now we've really limited that developer down. Maybe he's only got read-only access, right, to specific pieces, if at all, right? We're going to track all of the cluster changes using Git, right? Because again, this is configuration as code, so everything's going to be checked in, right? And if we're a wise DevOps team, we're going to use one of the GitOps tools like Argo or Flux, right? And I've been using Flux a lot, but Argo has a nice graphical user interface. I use Flux a lot. Flux will go to the Git repository, pull the Git repository, look for changes, and then apply them all for me, right? So now as my DevOps team, I can go make all the changes, and every time I push a change, it's going to push the change directly to the cluster for me, and even my ops guy doesn't need to run kube control and start making changes to things individually, right? All that happens automatically every time he does a commit to Git, right? Great, we're making a lot of progress. But we still have an issue of sort of observability, right? If you gave the developer read access, he can basically go, what are my pods in my namespace, right? Whichever one the developer is using, and then go look at the logs for the individual pods in his namespace, right? That's pretty much all he can do, right? That works, but it's not great, right? It doesn't, first of all, it doesn't give you a lot of monitoring in the ops team, and it doesn't give your developer a lot of monitoring, you know, in what he's doing. He's got to constantly be checking that or tailing the file with kube control. So we want to improve that, right? We really want to bring up some observability tools. There are a bunch of standard ones out there, right? You know, Elk, Grafana, Loki, Prometheus, right, are all monitoring tools that can capture the logs, centralize them, make them searchable, give you a user interface on top of them for getting at them and making queries and labeling what's in them, right? At that point, we can pretty much remove the developer's access to the cluster altogether, right? He doesn't need to do anything directly, right? He can have, there's Grafana can tell him what, if you give him some Grafana access, he can see what's running in his clusters and he can use those tools instead. He doesn't need to do it directly. So give him access to the observability tools and not directly to the cluster. So now your developer is being successful and he's starting to push stuff out, but he's starting to get a lot of services, right, running in his cluster. It's not just one pod talking to a database pod, right? And we want to take advantage of all those cool features that Kubernetes gives us for load balancing and failover and all those kinds of things, right? So we need to get more sophisticated with how we're going to deploy stuff, right? Otherwise, we can't scale the services and we're not going to get the benefits. So at this point, we're going to start talking about replica sets and deployments, right? So now instead of having my service just basically run one of a pod, it can run multiple pods for me, and I can put a service mesh in place that knows how to route traffic to the multiple pods that are the multiple copies of the same services that are running, right? And so if one of them is down, or if we're doing an update, it'll do what's called a rolling update. It'll shut one of them down and then update it, and then shut the other, and then switch the services over to that one, and then shut the second one down, and then update it, and now you've done a nice update to all your services without having any downtime, right? So Kubernetes can do all that, and the service mesh is this routing tool that lets you connect all the services in all your pods together, right? And services meshes give us some more capabilities here, right? They give us some more observability because they can typically log all the operations that are going on. So we're going to get tracing, we're going to get load measurement, etc. We can turn on MTLS in a service mesh, right? So now, instead of those pods that were those services that were basically open and able to talk to anybody, right? Now they're encrypted, and now they do mutual authentication between each other, and now we know the service is talking, that the pod is talking to the correct service, and the service knows it's talking to the correct pod. So MTLS gives us a tighter integration here and encrypts the traffic and all those other useful things. So our service mesh brings a lot more value to this as we're growing up our capabilities in our cluster here. Now, one of the things, this may not everybody's going to need this, but the next thing that we're talking about here is sometimes you have a service that does need to talk to the Kubernetes API, right? Let's say I've got a batch job that needs to run every day, and my application's going to wants to go start up a new pod to run it, right? So to do that, my service, my application running in the cluster needs to talk to the Kubernetes API. So that's where service accounts come in. And Kubernetes does manage service accounts, right? They get created by default. There's one default service account in every namespace. And by default, that service account cannot talk to the API, the Kubernetes API. But service accounts are K8s objects, right? So you can create them and manage them. They do get role-based access control. And again, that can be defined in the pod YAML. We saw that in the bottom of the pod YAML when I looked at it. There was a mount of that service account, right? All the information you need that. So that gives you that ability and locks it down to specific pods. So now our cluster is a success. Our one team running inside of the cluster has its people doing its things and it's working together. And now I want to start adding more teams in my company that want to share our cluster and get advantage of this, right? We're already going to separate them in their own namespaces because we were doing that with all the development teams, right? But nothing in a Kubernetes cluster, everything in the Kubernetes cluster is accessible and has a dynamic name that's created. So if I go to my service name.service.cluster.local, I can get to it. Even if it's a different namespace, sorry, there's a namespace in that, we're in that myservice.namespace.svc.cluster.local, right? Would let me talk to any other namespace and their services that are running in there, right? It's not limited between namespaces. And that's, again, very flexible solution and the easy answer. But again, if I'm trying to lock down a system and have more users on it, I probably don't want to do that. So now we start talking about network policies, right? So network policies allow us to essentially put firewalls between the services within my namespace and between and egress to other namespaces. So I'm not going to show you the definitions because it's getting too big and bulky, but it allows you to say this pod is allowed to talk to this service and it's allowed to talk to a different namespace and the service on that one, right? So we can get down to the point where your ops guy has now locked it down so that your team has 1 or 2 namespaces. We've configured it so their pods can only talk amongst themselves, right? And can't talk to the other parts in the company. So that's great. Right? That's starting to be a pretty reasonable solution at this point. You can go one step further. I didn't put a slide on this. You can actually completely virtualize the cluster, and there's a Kubernetes version for making individual clusters that you can hand out to more teams. Right? That's an even more isolated version rather than sharing namespaces and trying to put the firewalls up between them. But that also works as a different solution. You end up having a cluster that just manages the other clusters within the. It starts to get a bit inception all the way down, but that works too. All right, so what did we go through in all this? Well, we're tracking all of our changes in all of our YAML files. We know everything that's happened to this cluster. We have a complete auditable log of all the changes that were made to the systems. We've limited user privileges so that only the people that have the most restricted rights to what they need to do their job, right? We've limited the pod capabilities so that you don't have, so a leak in a single container can be restricted to what it can get to. We've encrypted all the traffic within the cluster. We've encrypted the traffic from outside into the cluster. We've managed our secrets in some way that's reasonably long-term manageable, right? We've added some observability and tracking and alerting by using those third-party applications that we added to the cluster, right? So we can look for unusual, anomalous behavior and track things that might be going on within the cluster. And we firewalled all the traffic between the namespaces in the cluster. So at this point, you have a reasonably secure, version. Of course, your container has to be secure, right? But in terms of the operation practices of running that container, we've locked it down pretty well. So that's my talk. Open for questions. Yeah. So the question was, now that we've got all this stuff as infrastructure as code, what do we do to monitor and track changes to the infrastructure pieces and make sure that our rules don't get violated? Yes, there are, right? I didn't mention them. I didn't mention admission controllers, which is another bit in here that controls which YAML files that the cluster will accept, but that's another control that could go in here. But yes, there are tools that will check the YAML itself and apply rule sets to them, schema rules, et cetera, and validate them. I haven't gotten that far, right? Again, a lot of this is my home cluster, and then a lot of this is the big corporate stuff that I've done, and then I'm not necessarily the DevOps engineer on the big clusters, all right? So I'm mixing between them. But yes, those tools do exist, for sure. What else? All right, I don't think there's any other questions. Thank you.